All right. Well, I want to make a short video to kind of spur you on the project. I'm actually working on it myself, and I spent a lot of time. So first off, let me just show a couple of things. So on the website, and let me bring this up, and I'll bring this up over here. So Micro 2 and the what is content? Where is it? There. I haven't gotten this one really fixed yet. Okay, so anyway, so if you go down to the videos, the YouTube links, and you scroll down to the bottom, you'll see a couple. So I spent a lot of time. So the first thing I tried to do was set it up so that the system, so we could use the system tick, and I spent a lot of time getting that set up. Actually, it wasn't that difficult. It's pretty easy to set up, but the thing that was problematic was that it didn't run at the right frequency, which was really disconcerting. And so I spent a lot of time trying to figure out how to check the frequency when I realized it wasn't working right. And then when I saw that it really wasn't, when I confirmed, yes, absolutely, it's not right, I then had to figure out how to fix it. So it took a while to do that. So I spent a lot of time getting the system tick so it would tick every 1/10 of a millisecond. And then I tried to use the system tick and run the code to calculate the PID controller every 10 milliseconds in hopes that I could then have that somewhat synchronized with the PWM. So I put on the scope and I did exactly that. I had it set up so that
this is my attempt to
let's see. to
try and sync.
So you can see, and I don't know if you watch this video. I made a little video and talked about it, but here's the scope. So the yellow tracing is the system tick, and it's generating a little spike every 10 milliseconds. The pulse period is exactly from the start of one pulse to the start of the next pulse is exactly 10 milliseconds as well. But as you can see, they're not both exactly 10 milliseconds, because if they were exactly 10 milliseconds, they would have a fixed relationship with each other, but it actually shifts a little bit. So one of them, I'm not sure which, is getting cheated a little bit. It's either a little bit faster or a little bit slower, whatever, I'm not sure. But in any event, it's not running at exactly a 10 millisecond pulse. Okay, so I realized that idea was bad. I could have put in some delays and played around with it and tried to get my my software to try and get this count a little better, but I was afraid no matter what I did, I'd still have a little delta in time that would cause this slow frequency, this slow phase drift, essentially. All right, and you can see they're pretty close. These yellow spikes are placed almost exactly the same as the blue. The leading edge of the blue in any event. Okay, so I gave up on that. So the next thing I did, I decided to try and figure out how to actually look at the interrupt flags that are provided in the PWM module, and that took a long time. And then after I figured it out, I had to play with them, and then I had to have some way of outputting the synchronization of one with the other, and anyway, I finally did, and then I made this video, and you can see. So in this video, I'm toggling
so in this case, you can see.
Toggling an output pin, and that output pin is then totally locked with the PWM because it comes from the PWM module, and it is the flag that's set at the end of every PWM pulse period. So this is fine. So what I do, I wait until that flag is set, and then I drop through, I run the PID loops, and I go back around and I wait until the next time it's set, and that allows me to basically generate an update during in between the start of each PWM cycle, and so that the data for the next cycle is available before the next cycle starts, and the reason that's important is you write the new duty cycle into the duty cycle register, which is the mod register in this case. You write it in, and when you write it in, nothing happens until the start of the next cycle, and then it transfers the contents from the mod register to the actual PWM output function, or there's a buffer on that register, I guess. Anyway, and that's so you don't change anything in the middle of a PWM cycle. Okay, that having been said, so that part's working now, and so that's good. So you can look at those two videos; they're kind of fun to look at, and I have a little accompanying talk, but you kind of seen them now. So if you haven't looked at them, that's fine. Okay, so where are we? Well, so I did put some code on GitHub. Let me pull that back up, and I'll go to GitHub. Let's see, I didn't have it on here. No, but I think I can do. Okay, and then so you have to go to docmode99/micro2, and that's the stuff on GitHub, and so if you go to that, which I think you just have to click on it, then there's the original tilt2 zip code zip file with the code in it, and then now there's this file, and so there's a couple of things to say about this. First off, let me just show you. I will pull up NCU Expresso. So if I shrink this back down so we can see what we're doing here. So if you go over here to our project and you right click and you go down to properties, you get this interesting menu with all sorts of stuff. And if you go into build and settings, so first off, so preprocessor. So there's a whole bunch of, I had to play with these commands. So one of the things I wanted to do was to print out the values that my PID controller was generating, so I could make sure that what I was getting was what I thought I needed, and then also I needed to do that so I could transfer it from the coordinate system that we set up on the panel, which is 0 to 2000 on each the x and the y axis, to the servo output, which basically runs from something like 75 to 225 or 85 to 215 or maybe even 90 to 210 or even 100 to 200, with the middle being roughly 150. Now the middle totally level is not quite 150. You could play with that by using the little the actuator rods, which are threaded, and you can unthread them, and you can't get them any shorter, but you can make them a little longer. And in doing so, you might be able to get it level when you're actually set at 150. But realistically, you're probably going to have to modify that center point a little bit. Well, anyway, so the problem is that your raw data is going from 0 to 2000 on each axis, but your actuator information needs to go from, say, 90 to 210, with the center at 150. And I've actually done this. This is my third, doing this from scratch, basically. And all the other times, everything was set up on a -1 to +1 basis, and it made this mapping a whole lot easier from your PID controller to your servo controls. And we mapped the tilt table. -1, -1 was the minimum values for x and y, and 1, 1 were the maximum values, and the total range was -1 to 1, and the 0 and the very center point was 0, 0. Well, we didn't set it up that way this time, and that's fine. I don't care. We're going to make it work. But it turns out there's a little bit of math that has to be done to translate it into the right thing. And on top of that, if your servos are, and because all the servos are mounted different ways, some servos, when you put in 75 or 85, the servo goes down. That's what we expect. But in some cases, it actually goes up. and that's just because of the way the servo arm is mounted on the hub, and the way the servo is turned or not turned, and screwed into the tilt table base. So because of the variation in all the tilt tables, because we didn't do them all exactly the same, some of these servos work backwards, and so now instead of going from say 85 to 215, now you're going from 215 to 85, and so you have to make sure all your signs are right. So what you have to do is spend a little time and go through the math. Now it turns out I just started with your coefficients for your proportional coefficient and your differential coefficient and your integral coefficient. You should definitely leave the integral alone for now. Don't mess with that. Those coefficients, all the other times I've worked with them, they were in 0.001, 0.005, that kind of thing. So that's kind of where I started. And surprisingly enough, I then played around with other numbers and did things and eventually got it sort of working because I had all this problem with printing things out. It turns out that that it won't even print floating points until you do printf underscore advance underscore enable equals 1 in this little settings thing. And then you also have to do this printf float enable equals 1 for it to handle floats as well. It wouldn't even print out negative integers initially. So I've been pulling my hair out trying to get the printf to work. Now, it turns out there's some other settings. And it's just crazy, all the different things you can do. And I'm trying to remember, let's see which ones. So, yeah, let's see, let me pause it till I find it, because it may take me a minute here. Yeah, so it turns out there's also another page here where you have to check the box enabled print float. Oh, but notice these are all of the libraries you can use. You get to pick one. There's redlib, and I've yet to totally understand the difference between none, no host, NF. I know the semi-hosting has to do with this little window down here, down in here in the console. That's the semi-hosting console window, and they've set that up so unless you check differently, which we did because we don't want our output to go down here. We want it to go to a terminal window, so we don't have to use it with MCU all the time. Anyway, if you change your library to say what it was originally set on here, these are grayed out, which means there's no floating point capability in printf with these libraries. So anyway. So I went through these, and it turned out I clicked on one of these. I guess it was the NewLib and NewLib Nano, and I don't know. And NewLib Nano is a smaller footprint. That's one of the reasons they have it. And I don't know. I really don't know. But in any event, some of these allow you to set these things. And then when you do that, you click Apply and Close, and then there's another setting that comes up that allows you to go, restore defaults, because I got things screwed up and I was having trouble, so I hit restore defaults. Oh, don't ever do that, because when you do that, it changes some things, and I don't even know what it changed, but now I cannot compile my code in debug mode. I have to compile it in release mode. You say, what's the difference between debug release and debug and release modes? Well, if you highlight your project and you pull the down arrow either on this sundial, which says debug and release. If I select debug, if I select release and I compile it, it compiles fine. No errors. If I select, and you can do it on the hammer too, as it turns out. So I don't know what the sundial's purpose is. If I click debug and then I run this, I will get, a bunch of errors. I'm not entirely sure why. I get 2,000 warnings, but that's because I incorporated. I think I incorporated this legacy .h, and I think that's the legacy.h, and that was so I could use some of the old features, and it sort of works, but it generates all these warnings because there's duplicate entries for a lot of the things in the header file. because we actually also have a header file down here, and I forget if it's in the includes here. Nope. Yeah, here it is. Here you have the same thing here, and these are actually two totally different files. This happen to have the same name, and that's where all of the warnings get generated, because this file and this file have about 2,000 entries that are the same but with different. They define things differently, and so I put in the one header first. And anyway, you don't need to do this because I was kind of playing with things. But anyway, so that's how come it gets all these warnings. You can ignore that. But the 9 errors that it gets have to do with the changes that got made when I restored defaults. I don't even know what they were, and I can't really fix it. The only thing I could do is start completely over with one of the original copies, and then paste in the changes, and hopefully everything would be fine. It probably would be. I might do that eventually, but for now, it doesn't really matter because you're probably not using the debug features anyway. So just click up here, either on the sundial or on the hammer, and click release. And if you click release, it'll be fine. No errors. Kind of crazy. So there are a lot of features to this very complicated integrated development environment that I'm still trying to master because it's brand new for this semester, and I hadn't really looked at it at all until January. Okay, but I do think it's a big step up over CodeWarrior, and so that's good. That's the good news. Okay, so when you download the file off GitHub, then this file here will not compile in debug mode, and I think it defaults to that. So the first thing you have to do is switch it to release mode. But and maybe eventually I'll fix that, but not now. All right, so the other issue, going back to the code, so if we expand this, so a couple of things to talk about. So first off, at the very beginning of the program, here's where I set the coefficients for the PID controller. There's an integral, a derivative, and a proportional for the X controller, and there's a derivative, integral, and proportional for the Y controller, and that's fine. Initially, make sure you set the integral to 0, and you probably should set the differential to 0 too. And then what you should do is dial in some of the proportional, and then see how your tilt table responds. Now, in this case, if I modify this, and let's see if I can. I think I'm probably going to have to change this. Let me change cameras here, and I'll show you this. Let's see, and I need to turn on the light. So here's the. Oh, I put this down here. So here's the tilt table in all its glory. Okay, and I have to switch this, I guess. Okay, now. All right, there it is. Now, if I go ahead and get it cranking here, so that it's more or less working, which hopefully it is. So right now I've got it all screwed up, but this is a good test. So if you take your ball, or even just your finger, and you move it, now notice this doesn't go up. So my proportional is clearly not working correctly. Here it goes down instead of up, and here it goes way down, and here it goes down. So basically, it looks like it's working backwards. So I probably have a sign problem in both my X and my Y. And I've got some other problems too, because it's totally out of whack. Now I had it actually working, so it was bouncing the ball earlier, but I've changed a bunch of things, and now it's not working. So enough of that. But I just wanted to show that so you could see, how you can approach this. Oh. Okay. Go back to me, and I'll put me back over here. Okay, so now, okay, so anyway, so that's fine, and so that's a good test. So if you find that your table starts to move, so when you move the ball, it pushes up against the ball, you go to each corner and it pushes in every corner, then you know your proportional is working correctly. And then you can start playing with the constant a little bit, and you can make it smaller and lesser, and then you can put the ball on the table. Be very careful, because if it falls off and shorts out something on your board and blows it, that'll be bad. The freedom board is pretty well protected, but some of these pins up here still touch, and you can definitely maybe short if you land the wrong place on the controller. So just try and catch the ball if it comes off, and so it doesn't break anything. Or if you want, you can put something over here, but you don't. The other thing is, while you're working with your table, every now and then feel your servos, and if they're getting hot, unplug your battery and let everything cool down. If they're doing a lot of jittering, they will heat up over time, and if you get them hot enough, it'll break them. So not as much as it used to, because in the old days we were running them at 7.2 volts and through a 1 ohm resistor, and that just didn't work. They got too much current frequently. But make sure your power supply is set for 6.5 volts on the input, on the output, not on the input. The input should be 7.2 plus. If the battery is fully charged, it'll be almost 8 volts. Okay, so first of all, zero everything except the proportional, and then set that up. You can even work an axis at a time. You can even tape some little paper guardrails so that the ball can't fall off left or right. You can work on X, and then you can change it and work on Y if you want. And unplug the other servo once you get the table balanced more or less level in that axis. Okay, so the other thing I wanted to do, and I hope you can see this. Let me see if we can. I don't know if we can make it bigger. Let's see, maybe we can. Oh no, okay, that's not good. No. I don't know how to get rid of it. Okay, there we go. All right, so there are some things set up here. We also set up X and Y mins. This is for the servos. So I set this up so that it runs 85 to 215. So it won't push the servo lower than 85. It won't raise it higher than 215. Now, if yours is backwards, then the 85 is going up and the 215 is going down. You should adjust these. And you need to keep them symmetric around 150. So that when you send a command, if you want the servo to go down, then you can send the command 85. But that may actually be your upper limit. But fortunately, I changed the code, and this also caused me problems. If you go down and look at the set PDM duty function, you now pass it the X position, and again, I think here it's set 80 to 220. I'm checking that, so it's a little different number here. 80 to 220. Anyway, you send a value somewhere between there, and then you send a single bit. It's an unsigned 8-bit integer. If it's 0, then it takes this as the correct that your servo is mounted correctly, and 80 is down, and 220 is up, and still 150 should be the center. If on the other hand your reverse X value is a 1, then it'll flip that, and it just flips it by subtracting the X position from 300. But that's why you need to keep it sort of symmetric so that the center still winds up in the center. So so this does the mapping. So when you output your output from your PID controller, you want the numbers to be in the range of, say, 80 to 220. Now, if you look at this, and again, I'll change my camera here. So if you look at this, and now I'm gonna, oops, no, that's not what I wanted. Hang on here. It's got a button in a bad place. All right, so if you think about it, what you actually want, and I should have done a slide, but in the interest of time, I need to get this video done. So here we are. So if you think about it, you have, so let's see, I got it. Yeah. Okay, this is right. Yeah. So if you look at it, and I'll move this over so you can blow it up and see it. Okay. So if you look at this, so this is your tilt table, and this is the tape. This is the bench. Okay, and here's your steel ball up here, and here it is here, and here it is here, and then again same thing. So it's here, and then in this case it's there. So if the ball is, say, all the way out here at the end, you want a pretty significant rise, and let's call that about 200. And if the ball is a little, say it's a little closer, like here, I didn't draw that very well. If the ball is, say, here, and you want to move it to the center, then maybe you only want 175. If the ball's in center, then you want to have it level so it'll stay in the center and you won't roll it on past. Now, of course, the problem is once the ball starts rolling, it has momentum, it'll go past the center, and that's why with just proportional you get overshoot and oscillation. And then the same thing in the other direction. If the table's tilted this way, say the ball's all the way at the end here, then you want it down at, say, 90 or 85 or 80. So let's say you want it at 80, and then if it's maybe a little bit in between. So when I did this, I did 100 for the minimum. So this say the servo's at this end here, so it's all the way down, and here it's all the way up. So this would be 200, or actually I guess 220, and this would be 80. And then this would be I think I called this actually 100, and I called this 200, and then this I called 125, and this I called 175, and then level is 150. So those are the numbers I used, and then so I just made a little MATLAB routine. Let me get rid of this. Let me go back to. Okay, and we'll put me back over here. Yeah, no, screwed up my camera. It's so typical. All right, that's good enough. All right, so I did a little MATLAB thing, and so here, we'll clear this. Oh. All right. So anyway, so I put in these points. And I only did it for the x. I didn't do it for the y. So my calibrated points are 0, 500, 1,000, 1,500, and 2,000. So if you think about it, that's moving across. Say this is my touch panel over here. I start here. This is 0, 0. This is 2,000, 2,000. So on my x-axis, which is all I'm going to deal with here, in my x-axis I go from 0 to 2,000. So I start at 0, and then my next point is 500, the center is 1,000, then 1,500, and then 2,000. And then I go back 1,500, 1,000, 500, and finally back to 0. So that's my x. Now I also had to provide the last position. So I just assumed that this is probably not realistic at all, but I assume that I start off with both positions 0. So now when I move to 500, my last position is still 0 because it's that one. And then here, my last position is 500. Here, my last position is 1,000. Here, my last position is 1,500. Then when I'm coming back, my last position here is 2,000. My last position here is 1,500. My last position here is 1,000. And finally, when I'm back to 0, in my calibrated x value, my last x value is 500. So that's just because I'm stepping through it in steps of essentially 500. Okay, and I stepped from the 0, 500, 1,000, 1500, 2000, 1500, 1000, 500, 0. And my last position then lags behind. And so in this case, the delta is always going to be, except for the first value where there's the delta 0, the delta between the previous position and the last position is going to have an absolute value of 500, but it will have a sign that relates to whether the change is increasing or decreasing, because I always subtract my current value. I take my current value and subtract the previous value. I think that's how the controller works. Let me just check that. I might have lied there. No, sorry, it's up here. So here are the two PID controllers. Here's the X. And so to get the delta time, I take present time minus previous time, and it turns out because I've synchronized this with the PWM cycle, this number is always 100. I printed it out, and that unless you put in if you put in a lot of print statements, it slows the algorithm down so much that then you can exceed 100, because it goes through an entire duty cycle before it gets back around to wait for the next duty cycle, so you actually wind up with 100 plus something. But as long as you don't have a bunch of print, as long as you maybe just have one print statement, just fine, maybe even two. But if you do 3 or 4, you'll definitely take too long, because the prints really slow it down. It puts out 1 character time, even though it's using 115,200 baud, 115,400 baud. It's still slow compared to how fast it runs through this otherwise. Okay, so I get my delta time, and it's always going to be the same for, it's going to be 100, and it's going to be the same for X and Y. And I collect that time up here. So basically I set up some things, and then I have this infinite while loop here. And the first thing that it does in this infinite while loop, it waits on the flag in the TPM using this TPM call. And then as soon as the flag is set, the first thing I have to do is clear it, and they give you this function to clear it. But what that function does is it writes a 1 to clear it. And there are actually 3 flags, so that's why I have 3 hex digits, 1, 0, and 3. There's actually 8 bits involved. And the flag I'm interested in is bit 8, it's bit 8. And you can look it up in the huge manual and sort of see all this. Maybe I'll pull that up real quick so you can see that. Hopefully I've got it handy. No, let me pull it up real quick. It is. It's right here. Okay, I've got those black things there to block out the light so my face isn't so bright, but anyway. So I go down here to the TPM module here, and we have to go down to the appropriate register, and it's the status register. So it's the status and control register. There's one for every channel. So there's a TPM 0 status and control, a TPM 1 status and control here. Sorry, no, that's the channel. There's 6 channels in 0. A TPM 1 status control that just has 2 channels, and a TPM 2 somewhere here. TPM 2 status and control. Okay, so let's go look at the status control register. And if we do that, here it is. And you can see, let's see. Yes, it's this TOF flag. Yeah. So it's okay. So there's a status flag here, but there's also a status flag in each of the channels, and I'll show you that too. Now this is the actual hardware register. So here's your TPN1 control, TPN1. Here's TPN1 channel 0 status control. Okay, if we go to that register, then what you'll find is that you have some flags, and this CHF is the channel flag. There's a channel flag for channel 0 and a channel flag for channel 1. We're using 2 channels. So we actually have 3 flags. We have the flag in each of the channels status and control register, and then we have the flag in the status control register for channel for PWM 0 for the whole device. Okay, so how does that explain this? Well, okay, it doesn't, because the hardware registers aren't the way the program is set up. So I'm going to pause it and bring that up for you so I can. Okay, so if I switch from my main routine to the FSL underscore TPM.h module, you'll see that I have an enumeration for the channel numbers. And here's how the enumeration works. For the channel, for TPM 0, channel 0 through 7, the flags are set up like this. I have the first 4 bits are channel 0, 1, 2, and 3. The next 4 bits are channel 4, 5, 6, and 7. And then the 8th bit, which would be the 3rd hex digit, is the timer overflow flag for the TPM 0 status and control register. So you have so this enumeration is actually what we're writing to, and then they go out and somehow get this information from the appropriate registers and put it in here. I don't know how they do that. I'm a little confused, but I think it's, yeah, it doesn't even say. All right, and then if you go and you look at the actual code, let's see, it's down here near the end. Yeah, enable interrupts, disable interrupts, and you have to clear. No. Output compare, input capture, update edge level select, update PWM duty cycle. No. What we're actually looking for is not channel parameters, not setup, not default, the-init, not the init, get instance. Oh crap. Okay. Let me go back. I forgot what the name of the function is. It is TPM clear status flags. All right. So let's see if we can find that in the header files. I can't remember if it's here or here, but anyway, let's look here. So we'll do a Control F. Yeah. Okay, there they are, and then we'll go down here. Yes. So here's the function. TPM get enabled interrupts. Okay, well that's okay. TPM get status flags. There it is. That's the function, and it returns the status flags. So that's the function prototype there. Well, that's the definition of the function. And so status is the status. Then let's see, what is it? What comes up if we hover over this? Yeah, I guess. Oh, okay, I guess there is a status register. I didn't spend a lot of time figuring out exactly how they did it. I just, once I found out what I had to do, but maybe there is. I think there is maybe a register that puts this all together. Let's see if we can go back here. Okay, sorry. No. Okay, no. All right. Counter, modulo, channel M status and control. So I think they use this register right here. Let's look. Yeah. So yeah. So what they do? Okay. So here's where they get it. So these are bits 0, 1, 2, 3, 4, 5, and there's actually 6 and 7. but I think I'm in the wrong. So CH5. Channel 0, 1, 2, 3, 4, 5. Well, there's actually only 6 channels in TPM 0, not 7. But they went ahead and created. It's pretty amazing. They went ahead and created the enumeration includes all of them. So if we go through this again, sorry. You see they created channel flags for 8 possible channels, but our device can only have 6, and that's only in TPM 0. In TPM 1 and TPM 2, they only have 2 channels, but they still have 7. They have 8 possible flags, and that is why this is represented by 3 hex digits. One that covers the channel flag 0, 1, 2, 3. Next digit covers 4, 5, 6, 7, and the final digit covers 8, and that does come out of the overall one of the overall status registers for each TPM module. And again, there's TPM 0, 1, and 2 in our device, and TPM 0 has channels 0, 1, 2, 3, 4, 5, and we don't even have a channel 6 or 7, but that's why it works out. So in my code, when I'm doing this, I use the value 0x103 unsigned. So that puts a 1 in position 8, and then I don't do anything with channels 4 and 5, and 6 and 7 don't even exist. And then I do channels 0 and 1, I ignore 2 and 3, because we're not using them. So I have 1s in all the positions where we have to clear the flags. So you have to literally write the 1 to clear the flag, not a 0. You write a 1. And that's how this is set up. And this function does that for me. Now, if I wanted to, I could just write that register directly. And that's how things were set up in CodeWire. CodeWire didn't have some of this fancy stuff. But sometimes the fancy stuff makes it harder to figure out what's going on. Okay, so anyway, so there we are. And then I use the MCU Expresso way for toggling a pin. So I create a structure, which is right here, called GPIO underscore pin underscore config underscore T, and the name of it is systicout underscore config. And then that structure has 2 entries, whether it's an input or an output, using this enumeration to make it an output, and I think that's just a 1. And then the logic state, and I made out state a variable so I can change it, and then every time I come through, I toggle out state. So I'm actually changing this value. I declare out state within this case, and interestingly enough, it only has scope within this state, within this case, within this switch statement. Outside of this case and outside of the switch statement, it has no scope. The variable won't exist. If you try and reference it, you'll get unknown variable. All right. Well, anyway, and then I call. Then I call this function that uses this structure to change it from a 1 to a 0. So all I'm doing is toggling this pin. Now remember, you may not remember, but in CodeWire, we had a simple command. We could have GPO, in this case E underscore pin toggle output register, and we could set it equal to a 1 in any of the 32 positions that were actually real pins, and it would toggle wherever there was a 1. But that functionality is still there. We just don't have the nomenclature is not available to us unless you include that header file, which I did, and that's how come I get 2,000 errors. But anyway, I digress. Okay, so and then we so basically what this does, this makes us wait until the beginning of a PWM cycle, and then we drop through. And we drop through. The first thing we do, we get the new raw position, and then we get the time based on the sys-tick timer. But it's always 100. It always reads 100. The delta does, because, well, yeah, we get the present time. And yeah, we get present time. And then when we subtract present time from previous time, it's always exactly 100, because we waited until the flag was set, and then it hasn't been a tenth of a millisecond to execute this code. So it is always 100. And that represents 100 tenths of a millisecond, or 10 milliseconds. Okay, then we apply the calibration values that you established using you basically mapping your touch panel, and then using the code in MATLAB to generate your 3 conversion values that give you the calibrated X and the calibrated Y from the raw X and the raw Y. Okay, now you've got calibrated values. That's good, and you should print these out at some point with a print statement here before you do the rest of this. Make sure that when you put the ball or touch the 0, 0 corner, your calibrated values are very close to 0, 0. When you go up to 2000, 2000, your calibrated values are 2000, 2000. In the center, it's 1000, 1000, and at each corner, it's 0, 2000 or 2000, 0, depending on which other corners you're at. Okay. So then, now you're ready to run your controller. So for the X, the first time we do is we take the delta time is present time minus previous time. Well, present time was the reading that we took up here right after we dropped through, okay? Or wherever it was, here. Right? No, actually, it's right after we did our A to D conversion. And it does that, and remember, in our A to D conversion, we have set the A to D module up to average 32 samples. We sample the X 32 times and average them, and then we say, okay, we're done. And we go into the interrupt service routine and read the value. And then we set it up for the Y, and we read the Y 32 times and do an average, and then we generate the interrupt service routine. We go to the ISR, and we save the Y value. And this is done completely, with the exception of the ISR. The processor is not doing any of this work. That's all being done in the A to D module itself by hardware automatically, which is really cool. So we're getting an average of 32 samples. So these values are pretty good, and there's not a lot of noise in them because they've averaged 32 readings. Okay, so now we get the delta time, and again, it's always 100. So you can actually, if you get everything set up right, you can actually skip this step. And you could even argue that you don't even need to divide by this because if it's always the same. Then the first thing we do is calculate our error term. Our error term is the set point minus our current position of the ball, which is our calibrated X. So our X set point, which is 1000 always, minus our calibrated value, which is where the ball is now, which is wherever it is. And that gives us, this error can be negative if the set point's always 1000. So if our X is, if the ball's to the right of the center, it's going to be bigger than 1000, so it's going to be 1000 minus something bigger, which would be negative. And if it's to the left of the center, it's going to be positive. That's important because this then, the sign of this error term then gets folded in to our correction, and if our correction's off by a sign, then this is one place where you can fix it, although I don't recommend that. You could fix it. It's better to just fix it down below where you just change the sign. But you should make sure that everything is working like it's supposed to. Okay, so you run your numbers, and then you put in some print statements and print stuff out so you see what it's doing, and then you see what you have to do. Okay, so then that's our error term. That's going to be used with that error term is going to be used in two places. One place it's going to be used is with our proportional our coefficient. We're going to multiply that by our proportional coefficient, and then that's going to be the contribution to our overall output for the proportional portion. Then we generate this integral term, and notice this is summed. So when we very first start out, we zero the integral term up here, but then down here we're always adding to it. We're always summing it. And we're summing it up. We're multiplying it by the integral coefficient to sum it. Now, in this case, our coefficient is 0, so our integral term should stay at 0. But when we bring in a little get integral, if the ball is not right in the center, then this will slowly build up and move the ball to the center. And then once it gets close to the center, the integral term will start shrinking again. And usually it'll move it a little bit past the center, and then it shrinks it down, and then it moves it to the center, and then eventually it'll slowly oscillate about the center, and eventually the integral term will be whatever it needs to get it to the center and keep it there. And that's kind of like a fixed value. And then once that value is there, you don't add to it or subtract from it. It's a fixed adjustment. And this is what corrects for a steady state error in a PID controller. And you see steady state errors in your setup when you put something under the edge of the tilt table and take it a little bit off level, so the ball's not gonna if the tilt table's perfectly thinks it's supposed to be level, but it's not because you've tilted it a little bit, the ball will never be in the center until you turn on your integral term and it corrects for that steady state error. Okay. So we calculate this term, but we don't add it in. We don't add it in. Well, we add it in down here where we correct the output, but only if our coefficient is not 0. Now, in the first version of this, I put in the wind-up correction, and that screwed everything up because it immediately made, even though the integral coefficient was 0, it still made the integral term the minimum value, which I didn't want. All right. So anyway, so now we have now we're going to calculate the derivative term, the x derivative input. And so the way this works is you don't take the difference between the set point and the calibrated value, which we call the error. You take the difference between the current position of the ball and the previous position of the ball. And then you divide that by the delta time. Now in this case, you do want to make sure that this derivative term carries some weight, so that that it actually impacts your overall output. And so the way this is currently set up with a dividing by 100 delta time and multiplying this by this by say 0.001 or whatever, it's not gonna do anything. So this derivative term is very small, and you can see in the y-axis when I ran the code that I posted, I think, I don't know, I'm not sure which code I posted anymore now, but basically before I changed this and I actually had it sort of working, I had a lot of oscillation in the y-axis, and that was because the derivative term wasn't doing anything. The x-axis sort of worked okay, even though the derivative term there wasn't doing anything either, and I'm not sure why that was. All right. So anyway, so now we have the final equation of our PID controller. We take our proportional coefficient times our error. Remember, the error is set point minus your current ball position minus plus the integral term, if we have one, which in this case with an integral coefficient of 0, we don't have one, minus our derivative coefficient times our derivative calculation up here. Now, I put in this 7.2 plus 1.25, and these were the things I was adjusting to get my thing to work. Because you have to sort of multiply this. And why do you have to multiply this? Because the raw numbers here, the raw numbers are based on small coefficients, and potentially when the ball's near the, so what I want you to do is ignore my minus 7.2 plus 125. Just forget that, and you need to figure out what you need to do here to scale this so that the resulting output will be meaningful. And that's why I did this MATLAB thing. Okay, so here I have my positions, my current position of the ball, and here I have the last recorded position. So for the starting point, I say it's at 0. My last position is 0. So my derivative term is going to be 0 there. But here the derivative would be 500, right? And if I do xcal minus, let's see, what did I say? It's it's xcal minus the last input. Okay, so it's xcal minus this one. So 500 minus 0 is going to be plus 500. 1,000 minus 500 is going to be plus 500. 1,500 minus 1,000 is going to be plus 500. 2,000 minus 1,500 is going to be plus 500. But 1,500 minus 2,000 is going to be minus 500. 1,000 minus 1,500 and so forth. So when the ball is moving right to left, this derivative term is going to be, it should be negative. When the ball is moving left to right, wherever it is in the tilt panel, if it's, doesn't matter where it is, if it's moving left to right, it should have a positive derivative. Okay, so anyway, so keep that in mind. And then, so my error then is 1,000 minus this calibrated value. So I use the calibrated value two different ways. One way I use it to calculate the delta from the previous value, and the other way I use it to calculate the delta from the set point, which is the center of the table, which is 1,000, 1,000, the way we set it up, the way I set it up, and probably screwed up. And in my defense, I was trying to mostly use integer math, but I broke down, and then you start dividing things, and then now you have to have floats. So I have some floats, but I also have mostly integers. And I don't know, I probably should just multiply things by 100 or 1,000 and not use any floats at all, because this program, this integrated development environment, will not print out a negative float. Initially, it wouldn't even print out a float at all. Initially, it wouldn't even print out a negative integer. But if you set everything right, it will do the above, but it still won't print out a negative float. And I spent a lot of time going through the web and looking at people who were asking questions, and sure enough, that's right. It seems like it's screwed up. And then some of the, you saw all the choices in compilers you had there, or the libraries, and some of the libraries don't support any floating point at all. So I probably should have tried to do everything in integer math, and maybe I'll eventually get there. But right now I've got a little mixture of some floating point, mostly integer. Okay. So if you follow this, then now we have the error term and the delta term. And remember, the delta term is the calibrated minus the previous point divided by the time interval. So this, I just abbreviated that 0.01, so I have it in seconds. And of course that makes the number bigger. If you put it in 100 milliseconds, it makes the number smaller. You can of course change all that by how you set up your coefficient for your differential term. So if your differential coefficients are 0.001 or whatever, then you probably have to use seconds here. And so 0.01 makes this a bigger number, and then you multiply by that, and you actually get something that's more than 0, or more than point something that works out to be 0 when you have integers. Okay. And so remember, our differential coefficient here is 0.001, so this isn't going to make much contribution initially. All right. So then how you calculate it? So I have my proportional component for my output, which is my proportional coefficient times my error, and then I wanted it to be in the range. So I have this goal. My goal is that when I'm at 0 on the extreme left of my touch panel, I want to have the servo set at 200 so it lifts fully up. When I'm at 500, halfway to the middle, I want it to be halfway between full up and level. And so I put it at 175. When I'm in the middle, my proportional term should generate 150, telling it to level the table because the ball's in the middle. No, there's no error. And then when you're on the right side of the set point, then I want it to be going into down position to try and bring the ball. Now the ball's on the right side, so I want to bring it back to the left. So I want to lower the left side. So I'm affecting the left side. At least on my touch panel, that's what I'm doing. Yours may work the other way. In any event, but I think we set them all up like that, actually. Think the servo's on the left and the servo's on the bottom. So, yeah. All right, well, anyway, so this is my goal. So then I just had to look and see, okay, what do I need to do to modify the proportional term to get it to generate these values, given these sample points and given these given the coefficient here. So that's what I did, and when you run it, my proportional coefficient then generates 200, 175, 150, 125, 100, 125, 150, 175, 200, just as I had for my desired. Okay, and my derivative then, my derivative, I can see right now it's confusing me. So when it's going left to right, my calibrated should be bigger than my previous position. So this really should be positive. So I'm confused why I got the negative. So I had 500 minus 0. Why is that minus 50? Oh, because I'm subtracting it, and I put a minus sign in front of it. So I guess I probably shouldn't have put the minus sign there. What I should have done is take this out here and put it in here. But obviously, it doesn't matter where you do it, really. But now it should work correctly. All right, so now my derivative term, it's 50. I want to subtract that 50 from my 175 to try and affect. Now the question is, what should this be? And that's a good question. I don't know. This is where it becomes very empirical. So the first thing you want to do is you want to get the proportional working correctly, and you want to check the math and make sure it's doing what you think it should be doing. So the numbers that I have currently here, times 7.2, 125, I need to change those because those are completely wrong. Okay, so ignore that and do some of your own math and figure out what you should put in there. But the whole idea then is to get the proportional working exactly right, and then make sure that your derivative is sort of in the ballpark with something that's meaningful, but you don't know if this is too big or too small. So now we have to go in and we have to, that's when you start playing with your derivative. So the first thing you do is you make the derivative constant, the coefficient 0, and you start increasing the proportional till you get a lot of oscillation with the ball. It might even be able to keep the ball on the touch panel, but it'll be oscillating, like a ship in a bad storm. But then you get to that point. Now you can bring in the differential, and you need to make sure that the signs are correct so that if this is a positive 50 and we subtract it from 175, we should decrease the elevation of the table to slow the balls rolling toward the middle from the left side so that it doesn't roll way past the middle and off the other side. And then you just slowly increase your derivative coefficient until you take out some of that wild oscillation. And then you go back and add in a little more proportional to give it a little more kabang when you roll a ball onto it, so it's going to respond nice and briskly. And you just kind of work with it a little bit at a time until you're happy. And you'll find that you can fiddle with them until you're blue in the face. But at some point, with a little bit of work, you'll get it so it balances the ball, and it's and the ball will stay on there. It's surprisingly, even with wild oscillations, it can often keep the ball on the table. If you have a fairly tight loop and you've got reasonably not very noisy data, it actually can work. If you've got a lot of noise in the system, Katie bar the door, because then you have to have your PID controller really tuned up, or you probably can't keep it on in any case. Okay, so we're just over an hour, and I think that's enough. I hope this gives you enough ideas about how you should pursue this, and you're going to have to look at this code and fix it. And unfortunately, in my haste to try and get something working, I made a bunch of changes here and a bunch of changes there. So I started screwing around with it there, and then but remember, right now, your output function, your set PWM duty, that function, which is right here, that function checks for a maximum of 220, a minimum of 80. So it's going to keep you in those bounds. It won't let you lower the table more than to 80, won't raise it more than 220. And you might want to tighten these numbers up. Maybe you only want to go 90 to 200, or sorry, 90 to 210, or maybe even 100 to 200, like I did on my MATLAB file. But you probably want this to be symmetric so that the middle is always 150 or close to it. So you can basically convert a servo that's working the opposite direction to still work correctly and still have the middle be the middle. Okay, so leave this function alone for now. I wouldn't suggest changing it, except you can change the max and mins if you want. But this equation down here works out to that works pretty well to reverse it if you've got a servo mounted the opposite way, so that it goes up when you give it 80 instead of down. All right, and all you have to do is go up here to setting to function 2 test servo, and it says X servo low, then Y servo low, X servo high, then Y servo high, then both level. So if you punch 2 and you watch what your tilt table does, you will know if your X servo went down first, and you'll know if your Y servo went down first, and then you'll know if they went up last and finally level. If they're going up first and down next, then that servo's backwards. And it could be that one's backwards and the other's normal. And it could be that they're both normal. It could be they're both backwards. So run that program and see which they are, and then change that coefficient. When you call this, mine are both backwards, so I'm calling it with a 1. So when I call it 151, it still sets it at 150. But when I call it 81, it sets them both all the way up, even though 80 is supposed to be down. But my servo is working backwards, and so the 1 flips it so that it actually does go down. But if it goes up correctly, then make the 1 a 0. And again, if your X is normal and your Y is abnormal, then make the X a 0 and the Y a 1. But both mine are backwards, so that's why I have 2 1s. So I would suggest you not change this down here in this function. Just go ahead and use that, and make sure your signs in your PID controller comport with that. So it doesn't matter whether you output, as long as you know that you want the output to be 80 when the ball is on the right side of center, then if your servo works backwards, you just have to put a 1 down here and everything's hunky-dory. So focus on this part, and don't and check your servos, and then just put a 1 or don't put a 1, depending on what you need. Same thing here. Okay. All right. With that, I will, and I didn't change. I don't think I changed. I didn't update these functions here. Did I? Yeah, I did. I made all mine go backwards, and now when I run 2, it works correctly. But you probably should put 0s here to test it, and then if it works correctly with 0s, then you know your servos are normal. If you switch them to 1s, and it works correctly, then you know they're backwards. And if one's backwards and one's correct, then you have to play with that. All right, I think that's it. I'm going to quit. I will promise to get this code probably late next week. I should have some really, some code that's working well, and that'll be great. All right, with that, I'm going to quit, and I will see you in lab next Thursday.